Vado. Okay, good morning and welcome to the last of the 4 lectures I'm giving here. Today we will continue the discussion we started yesterday about Boltzmann equations, and we will explore more the second case of the two that we listed yesterday. So remember, we started with the idea of, let me remind you our starting point. The starting point was in this plot where we have y chi defined as the comoving number density as a function of x, which is the inverse temperature, okay? Well, we can, of course, draw here the equilibrium distribution, easy, okay? This is equilibrium, it's a Maxwell-Boltzmann, and around x equal 1, you see the what you expect, the exponential suppression in the number density. This is not really the number density, it's a ratio between the number density and the entropy density, but the entropy density is T cube, is a power law. So you still suffer an exponential suppression, okay? And then we said, okay, but this is the equilibrium. If dark matter stays always in equilibrium, today we expect to have basically 0. So let's see what happens. And in the freeze out, we discussed from a qualitative point of view on Monday. The understanding was this. So you stay in equilibrium as long as interactions are enough. And for values of x around 25, you decoupled. And the brutal approximation we made was this. Okay? So you are either coupled or completely decoupled. So this is what we call instantaneous decoupling. Okay? Now, of course, this is not what actually happens. In particular, the first derivative of this function is continuous. And yesterday, we developed the mathematical tool to investigate this part of the plot. There is not much to say here or here, okay? When you are in equilibrium, you are in equilibrium, you know the solution. When you are decoupled, you know the solution. It's a constant function, okay? So really, the point of the Boltzmann equation is to investigate this part of the plot, but it is very important because we saw that actually there are post-freeze out annihilations that deplete a bit more the number density, and so the constant value you get is a bit lower. Because even after what we call freeze out, even after the moment where gamma is equal to h, dark matter and anti-dark matter find each other. Not enough to stay in equilibrium, but enough to deplete a bit the number density. Not by much, okay? So that's the motivation. And so yesterday we started with this motivation and we derived the so-called Boltzmann equation, which is a concept that goes beyond, of course, cosmology and tracking the dark matter relic density. It's something that the first time we saw it was not in cosmology, probably was in the class. And the rough, well, not rough, but the schematic way to write the Boltzmann equation is this, okay? So it is an equality between two operators acting on the distribution function of dark matter. So distribution function of dark matter, f chi. This looks more like an x, but okay, chi. Let me try to do that. Okay. So remember, cosmological principle, the universe is homogeneous and isotropic. Chi cannot depend on the position, and chi only depends on the size of the spatial momentum or the energy. We have the dispersion relation connecting them. Okay, so I use E here. And then, of course, it depends on time. And we know also that for each time we can find a temperature of the bath. So you can also say function of energy and temperature. This is a phase space distribution, and the equality between these two quantities, these are operators, so they act on the distribution function. And the one on the left-hand side is the so-called Liouville operator, okay? And basically, the best way to think about the Liouville operator is to say, okay, the Liouville operator is something that gives me 0 once it acts on the phase space distribution in the absence of collisions, okay? So it's a geometric effect. It describes the geometry of the expanding universe. If the universe is not expanding, the Liouville operator just tells me that the time derivative of f is 0. The f is constant. If there is no expansion and no collisions. If nothing happens, nothing can change. I gave you the expression yesterday for this. We did not derive that because it would have taken too long. But the derivation is actually very nice because you take the Liouville operator, the standard one you learn in StatMech classes, you write it in a covariant way, in the language of general relativity, then you put all the Christoffel symbols for the Friedman-Robertson-Walker metric, and then you see that there is a correction proportional to the Hubble parameter. Okay, so it's a very instructive derivation that I will provide you in the notes. But what we did yesterday, and we did this calculation explicitly, we took this kind of integral that we will take, and this is over the momentum, the argument of the, even though it depends on the size, so we went to polar coordinates, if you remember, only on the modulus of P. G chi is the number of internal degrees of freedom, because if we want to eventually get the number density, we have to account for the multiplicity. And then we integrated this over E, and we found explicitly this result. Okay? So this was, even though we did not give a complete derivation of the Liouville operator, but starting with the result I gave you and computing this integral gave us something that made sense, okay? Because we saw that the vanishing of this combination implies that n chi times a cube is constant. So the comoving number density is constant, which is exactly what we expect in the absence of collisions. Okay, so that takes care of the left-hand side. Now let's go to the right-hand side, and then we computed the collision operator. And again, as I said yesterday, we should expect this collision operator to be a sum, a discrete sum over all the possible number changing processes. So all the processes that change the number of dark matter particles. And so the one we focused on yesterday, which is not the only possible one, of course, but it's a good one to start, is this one. It's a process, and please notice that this arrow goes both from left to right and right to left, because eventually we will assume equilibrium, so the reaction happens in both directions. And you have that two bath particles. These could be electrons, muons, Ws, top, Higgs bosons, anything belonging to the standard model, or even something beyond the standard model, but in thermal equilibrium with the standard model itself. So they can find each other and produce chi bar. Okay? We are assuming that the dark matter is something like a Dirac fermion. So particle and antiparticle are not the same. If it is a Majorana fermion, you would have here chi, and there will be some factor of 2 to take care of. But let's discuss this case. Okay? And so we eventually wrote down the collision operator for this case. And let me write down the moment where we stopped. Well, not where we stopped, but where we stopped before we defined the freeze-out situation, okay? So, by the Boltzmann equation, I know that this combination must be equal to this, okay? Why? Because L is equal to C. This is the integral of L over E, so it must be equal to the integral of C over E, okay? And what we found yesterday, and remember, we assign four momenta P1 and P2 to the dark matter particles, and chi1 and chi2 to the bath particles. We have phase space integrals eventually, so we have to do that. So we have G chi d3 P1 2 pi cube 2 e chi. And then I will not rewrite all of them, okay? So here you have, I gave you the expression yesterday, phase space integrals, okay? Over what? Over all the momenta of the 4 particles participating in the process. So you have, sorry, here P1 and P are the same, okay? So I'm identifying a P1 as the argument of the distribution function, okay? It's okay, it's an integration variable. I can change the name as I change expression. Now, what is interesting is what goes, so there is an integration of something, and the point where we stopped yesterday after some assumption was here. There is a delta function with the appropriate factors of 2 pi to ensure energy conservation. There is a square matrix element. There is a product of the distribution function f1 and f2, and of course they depend on k1 and k2, or the energy of the bath particles. And then there is this annoying piece, let's say annoying, okay, P2. Okay. Okay, so that's basically where we stopped yesterday. And what did it take to get here? So this is not the most general form of the Boltzmann equation. If you remember, we had to assume that we could neglect quantum degeneracy effects. So every time we had 1 plus or minus f, we just replace it by 1. We assumed CP conservation, so the matrix element, the square matrix element for a process and the inverse are the same. That's why I could collect them out of the parentheses. And then basically we stop there. These are the assumptions we need. And following with a suggestion for some of you yesterday, I even left the dark matter distribution in principle different from the one of the anti-dark matter distribution, because it's not an assumption that is needed, okay? So yesterday, after we assumed CP conservation and after we assumed to neglect quantum degeneracy effect, we also made the assumption that Fk and Fk bar were the same. And then we identified the freeze out as a situation where you have kinetic equilibrium. So kinetic equilibrium means that Fk or Fk equilibrium is the same as the ratio of the number densities, okay? And so if this is equal to the ratio of the number densities, you lose the momentum dependence, because the number density is an integrated quantity. You take it out of the integral, and then what you end up with is actually something that gives you an ordinary differential equation, okay? So let's write the freeze out Boltzmann equation. The freeze out Boltzmann equation that we found yesterday is d and chi dt plus 3h and chi equal to gamma chi 1 minus n chi square, let's say n chi over n chi equilibrium squared, okay? Good, and what is gamma chi? Gamma chi is what we call the interaction rate, and it is proportional to, I will be more precise here, it is proportional to the equilibrium number density squared times the thermal average of the cross-section for dark matter annihilation, okay? So I want to start from here because I want to discuss something that I didn't tell you yesterday, okay? For this situation that will be very useful for freezing, okay? So to get from this expression to that expression, if you remember, I had to replace F1, F2 both at the equilibrium with the product Fk, Fk bar both at the equilibrium. Why I use energy conservation, and the Maxwell-Boltzmann distribution as the energy in the exponent, so I could do that, okay? But what happens if I don't do that, if I use this one? I can still do that, right? There is no reason why I cannot compute this. Once I guarantee that there is kinetic equilibrium, I take this very annoying square bracket out of the integral, but then I can do the integral with this form, okay? And so there is also an equivalent way to write down, let me call them N1 and N2. Okay. So there is an equivalent way to write down the interaction rate that it doesn't feature the equilibrium distribution of dark matter, but it features the equilibrium distribution of the bath particles. And instead of having the cross-section for dark matter annihilation, it has the cross-section for dark matter production. So you may recognize the detailed balance principle, okay? So in equilibrium, these two rates are the same, okay? And so this second expression will be more useful today, okay? So when you typically do calculations for dark matter freeze out, this expression is the one that is usually employed. But once you do freeze in, as we are about to do, this expression is more useful, okay? And all I did was to compute the thermal average by keeping F1 and F2 instead of replacing them with Fk and Fk bar. Okay? Okay, so this ends the review of freeze out, but I wanted to review what we did yesterday, and I also wanted to introduce this important concept. Why will it be important? Because freeze in corresponds to the other situation where this Boltzmann equation, which is integral differential, becomes ordinary, okay? And the reason why this equation becomes ordinary is not because we replace ratios we can take out of the integral. In the freeze-in case, we just ignore this, okay? Why are we allowed to do that? It's an assumption. This is true if Fk is always much less than Fk equilibrium. So this is true if dark matter particles are so weakly coupled to the bath that they don't even get close to being thermalized. Okay, so we are talking about extremely weakly coupled candidates, more weakly coupled than WIMPs. Okay, WIMPs, in spite of the W, which stands for weakly, weak interactions are enough, they are enough to ensure thermalization. Here we are talking about something with interactions much, much smaller than weak interactions, okay? So by the time you accept this, then you are in a situation where you have to compute the same integral as yesterday. And, you know, the Boltzmann equation for freeze-in is this, okay? The Boltzmann equation for freeze-in is even simpler, where this gamma chi is only a function of the temperature, okay? So in the case of freeze-out, we have a differential equation where the unknown function is n chi. A differential equation, there is something unknown, which is a function, and this function is n chi, appearing both on the left and on the right, okay? It appears also on the right. This is something we don't know, we have to find. Here, it doesn't appear on the right. So this is a hint that the solution will be even easier in this case, okay? So what is the physical picture here? The physical picture is that we derive this equation just by taking a limit of the most general one, okay? Now let's imagine what's happening in the early universe. What is the situation that gives us this condition here, okay? The situation is the following. You basically have inflation, you have reheating. Reheating produces a thermal bath. This thermal bath is made only of standard model or any particle that goes in equilibrium. This is an assumption. you could produce dark matter also through reheating. We are assuming that the dark matter produced through reheating is a small fraction. Otherwise, I would not call it freezing described by this equation. And then you have, in the freezing case, bath particles that can occasionally find each other, produce chi bar, but this event is so rare that you produce chi bar, but chi bar never find each other to give you dark matter destruction. So basically you have this. You only have this going from left to right, okay? And so this is what defines freezing. Of course, this is a specific realization of freezing. It's freezing through binary scatterings. You could also have freezing via decays, okay? So you could have by B1 that decays to chi bar, but then this decay, maybe it's a small branching fraction or fraction of the particle B1, and so you produce a very tiny amount of chi and they never go back, okay? So the idea now is to, so let's clean this. Yes. Absolutely, yes. So this is, if you want, a weak point of freeze-in, because for freeze-out, as we will see, both freeze-in and freeze-out give relic density that are only dependent on coupling and masses that in principle you could test in the labs, okay? So that's one of the strengths of these two scenarios. For the freeze-in, there will be an condition, which is infrared domination, which I will get to in a second. But if you want, for freeze-out, this is really nice, because freeze-out comes from a situation where you are in thermal equilibrium, and thermal equilibrium erases any memory of the past. So you don't care about the initial density for freeze-out, because you thermalize, and then who cares what happened before. For freeze-in, there is the assumption that as soon as you start the radiation-dominated epoch, which is what is usually called T-reheating, at the reheating temperature, the number density of chi is 0 or very, very small. Okay, so this is an assumption. This is an assumption, and if you accept this assumption and you take the coupling very, very weak, then this equation allows you to compute the density. But of course, if you produce a lot, and then maybe they thermalize, and then this is not this equation is not valid anymore. So I completely agree with this comment. Any other questions or comments? Well, if the heat temperature is large enough, yes, because gauge interactions allow you to achieve thermal equilibrium. So the only way you may not thermalize if the heat temperature is much less than the dark matter mass, so you have really a hard time to produce dark matter because this exponential suppression in the kinetic energy of the bath. So if you have a weak, in the sense of the weak interaction of the standard model, and you have a temperature as large as the dark matter mass, you thermalize. Any other question? Okay. Yes. Or what is the criterion? Well, let's say that you are always, of course, there is not a magic value above which is not freeze-in and below which is freeze-in, okay? So it's an approximation that will get worse and worse as you approach equilibrium. I would say that if the distribution function is at least 1 order of magnitude below the thermal one, then you have 10% squared in that case. So you have 1% correction, which is become acceptable, okay? So let's say a factor of 10 below equilibrium is what I would call freeze-in. Yes, but we will see that. But that's actually the condition for thermalizing. So if gamma chi approaches H, then you plug that in the Boltzmann equation and you see that n chi becomes equal to the equilibrium distribution. So you are not consistent anymore with the initial approximation. Okay, so you can double check that. Sorry, can you? Of chi? Well, you know, here you mean thermal equilibrium of these particles or of these ones? At the end. No, I'm not assuming thermal equilibrium. I'm not. Yeah, so if there probably there will not be time, but if there is time, I will say a few words about actually solving for the F. I will give you some reference. The last one appeared this morning. Okay, so we have fresh news on the subject. Okay, yeah. Other questions before I continue? Okay, so in the remaining hour, we try to quantify this evolution, and in particular, what we would like to do is to find the equivalent of the freezing line in this plot. Okay, so this is freeze out. This typical behavior that you start from being thermal and then you eventually approach a constant value. And I think yesterday during some of the student presentation we saw the freezing line being like this, okay? So you, as long as you achieve the same asymptotic value, you reproduce your matter density. It doesn't matter if you arrive here from above or from below. In the freezing case, you arrive it from below, okay? And we will understand the analytical behavior of these lines, okay, through that equation. Okay, so let's see what we can do to solve that equation. But before I do that, let me give you at least another case for this. I clean all the blackboards so then we can. Yes, while I clean, ask the question, yes. Not always, not necessarily. It could be, you know, there is these forbidden channels that can be operating, and you can also have a freeze out through annihilation to something heavier. You just pay a Maxwell-Boltzmann suppression in the rate, but it doesn't have to be lighter. It doesn't have to be lighter. Sorry, there is a? No. There is no, as long. Well, let me give you some cases, okay? So we can discuss explicit cases. So, for example, if I find a chalk longer than 1 centimeter, apparently not. Yes, no, maybe, okay. Okay, I can go on for 5 more minutes. Okay, so Boltzmann equation for freezing d n chi dt plus 3h n chi gamma chi, okay? So this is general. This is the general equation for freezing, and I emphasize once more that this right-hand side is only a function of the temperature, okay? So it will be very easy to integrate this equation. But before we integrate the equation, let's say, for example, freezing from decays, okay? So you could have B1 going to B2 chi, for example, okay? So what is the picture here? You are in the early universe, you have a radiation bath. B1 belongs to the radiation bath. B1 can decay to this state, featuring also dark matter particle, if decay rate for this specific decay channel, okay, is much smaller than Hubble, this process will not be enough to bring chi to thermal equilibrium. And so this will only happen from left to right, not from right to left. Thank you, Yuri. And so you will not thermalize, okay? Of course, it could also be V1 going to chi bar, okay? There are situations. And then you have to account for the multiplicity, but that's easy. Okay, so in this case, let's call it still the collision term, gamma chi. So what goes on the right of the Boltzmann equation, okay, is something that we could guess, and it is n chi, it's n1, let me write the result and then I will comment the result. So this is also a very nice derivation that we cannot do. So if you take the Boltzmann equation integrated over the phase space, and then you consider, instead of a scattering, you consider a decay, let's say this one, then you do all the phase space integral, you end up with this expression. So let's discuss this expression. It makes sense. It makes a lot of sense. Why? The amount of particles produced must be proportional to the number density of B1. Okay? The more decays I have, it must be proportional to the decay width for this specific process. So this is not gamma B1 total. It's the partial decay width to that channel. And so far, it's very easy to understand the appearance of this combination. There is also this ratio of Bessel function. Okay? You find this ratio of Bessel function when you do the integral of the phase space. Okay? So you may wonder why there are these Bessel functions. Well, there is a reason which is easily understood when we take this ratio of Bessel functions for temperatures much larger than the decaying mass, the decaying particle mass. So K1 of MB1 over T divided by K2 over MB over T. You take a Taylor expansion, you have a small quantity, the ratio MB1 over T, so you are going to temperatures much higher than the mass of B1. If I remember correctly, there is a 2 here, but I don't care about the 2, I care about this ratio appearing in the Taylor expansion. And this ratio is much less than 1, by assumption, because I am in this regime, okay? Does it make sense, this suppression? So this expansion is telling me that when the temperature of the bath is much larger than the decaying particle mass, then the production rate is very suppressed. Not very, it's suppressed specifically by the rate MB1 over T. Why? No, I'll give you one hint. MB1 is the rest mass of B1. T is the typical energy of the particles in the bath, including B1. So this M over E, I said the word gamma. Why? This is gamma of B1 to the minus 1. By gamma, I mean the Lorentz factor, not the freeze-in production rate. Okay, so this is the Lorentz factor. So I'm telling you that when the kinetic energy of B1 is very large, the production rate of chi is suppressed by a Lorentz factor. So this is what? It's a phenomenon that is known as time dilation, exactly. So the lifetime of B1 gets this suppression, okay? So this ratio of Bessel functions, to compute it exactly, you have to do the integral, but it makes sense, okay? Okay. Okay, so this gives you the Boltzmann equation for Frisin in the case of decay. In the case of scattering, I gave you already. What we try to do, well, we try to solve the Boltzmann equation at the very top of the blackboard by keeping gamma generic. Okay, we will not make any assumption of gamma, and then once we get to the end, we will try to figure out for the different cases what happens. Okay, so that gamma we have already seen two cases: the gamma for scattering, the gamma for decays. Okay, there could be other processes. Let's stick to these two examples, which are the most popular one. And now let's solve this Boltzmann equation, okay? It's very easy to solve this Boltzmann equation. Why? Because, you know, I have a left-hand side where I have the unknown function and the right-hand side, which is only a function of the temperature. And I know that if I define this, remember, then dy chi dt, okay, dy chi dt is 1 over s dn chi dt plus 3h and chi. This is something we derived yesterday. Okay? And make sure that, you know, I never remember if this s goes upstairs or downstairs. But then I say, okay, dimensionless, time. So this is an energy. This must be an energy. 1 plus 3 minus 1 energy. Okay, so through dimensional analysis, you can quickly see where to put the factors. Okay. Okay. Moreover, remember that we also derived this, and dimensions work. Okay. No. That was trivial. Okay, so this is also useful because the time is never a good variable to solve this kind of equation. Of course you can, but it's not so convenient. So once you put together, okay, these two, then you can find dy chi dt, where T is the temperature, is equal to what? Is equal to dy chi d time the temperature. Okay, and you see I know both of them. I know this because it's here, I know this because it's here. Okay, and so I end up with minus 1 over ht 1 over s, and then okay, so basically I replace this with the Boltzmann equation. Okay, so this Boltzmann equation is actually very, very nice. Why? Because it's simple. It's dy chi dt, where T is the temperature. Let's write it once more here. It's gamma of T in the numerator, a known function of T. And then I have what? I have the entropy density, Hubble, and T. Okay? So this is something that it's super easy to integrate now. Okay? And if I care about the value of y chi at some generic time, okay, at some generic temperature, okay, let's say that I have reheating. Reheating is, you can define the reheating temperature as the highest temperature when the universe was dominated by radiation, okay? So whatever your reheating mechanism is, there will be a point where the total rho will be dominated by radiation, and the temperature of the bath at that moment is the reheating temperature, okay? So I can integrate this equation between T reheating and any generic T, okay? So I have y chi of T minus y chi T reheating. So I integrate from T reheating to T, and then I find minus integral from T reheating to T in dt of gamma of T S of T H of T T, okay? Now, here is the assumption that we made at the very beginning. So if you remember, we said, well, there is an assumption, the one you pointed out. I am assuming that the initial density of chi, by initial, I mean initially in the radiation-dominated phase, I'm assuming that this is negligible, okay? So maybe if you have a reheating from the decay of the inflaton in the most, one of the simplest case, we are assuming that the branching ratio of the inflaton decays to dark matter is very, very small, okay? And so this is something that it doesn't have to be zero. It has to be less than the one I need to reproduce the observed abundance of dark matter, okay? So that's the assumption that we already identified before, and now we made it very, very clear, okay? We made it clear by saying, look, this has to go, okay? Okay, and then there is another little modification we can do to this equation. You know, this integral goes from TR to T because I'm going forward in time, okay? I'm going forward in time, so I'm saying, okay, I start from the reheating moment and I consider a moment after reheating. But of course, T reheating is larger than T, so I can, if you allow me, I can put a plus here and I can switch the integration extremes. And so you see now I have an integral that goes from a number which is smaller than the upper integration extreme, okay? And then all I have to do is to solve this, okay? And by solving this, I will find the solution of the Boltzmann equation, giving me the common number density at any moment, okay? So in the freeze-out case, you have to solve a differential equation. In the freeze-in case, you have a differential equation, but what you have to do is to compute an integral. There is no more than that, okay? And so this is, of course, simpler. Yes?
I think this is the point where you connected, getting rid of the y kind of reaching there to having it an input f much smaller than f. I mean, so there you're crossing it out because you want a closed formula for y, but it's not like consistency.
No, so these are two different assumptions. I want also this to be always below equilibrium. Okay, so I also want, if you want, this equation here, if you keep this term, is quantifying the amount of dark matter produced between reheating and the generic temperature. Maybe you can say at reheating I can have something already. Here I need to have more, or the same amount if gamma is equal to 0. But I require that both of these, and this is another assumption, both of these, and actually if I impose this, it's enough, this has to be smaller than the y chi equilibrium. So there are two different assumptions. The first one is required for self-consistency of the Boltzmann equation, that these y here, they never get close to equilibrium. The second assumption, and you're right, they are different, so let's discuss the difference. The second assumption, once I accept that I never get close to equilibrium, never ever going close to equilibrium, then okay, we can keep this, but then the resulting abundance will also depend on this unknown production at reheating. And the nice feature is that if you assume that this is subdominant, then the dark matter abundance today, which is extrapolating this to the present time, will only depend on quantities we know. There is M Planck here. And in this gamma, there are masses and couplings that are particle physics properties of dark matter. Okay? But you're right, two different assumptions. Being far away from equilibrium doesn't imply neglecting this. Neglecting this gives you a calculable relic density in terms of particle physics properties without any sensitivity to reheating. Okay. Any other question or comment? Mm-hmm. Okay, so be careful about gamma, because this gamma is not the gamma I spoke about before. I use a different gamma. This is a lowercase gamma, not capital gamma. This is the number of interaction per unit time and unit volume. So it has mass dimension 4. So this gamma over H is not dimensionless. Okay? But, if you take the entropy density as a fiducial comoving volume, you can say that this ratio here has to be less than 1. So there is a nice way to write this integral. Maybe let's do that. Okay? So d log t. And then now the quantity I put in parentheses is dimensionless. Okay? So you have gamma, gamma is mass dimension 4. This is 3 plus 1. This is the number of interactions happening per unit time and volume. This is the size of the volume. This is, well, the fiducial size of the comoving volume is related to the entropy density. This is the characteristics time scale of the expansion of the universe. You want this to be much less than 1. And if that doesn't happen, you realize this quickly, because if you solve this equation and you find that this y chi, now imagine you take this equation as the true equation describing the relic density. And then you solve, and you pump the coupling of chi here. You make this quantity huge. Then you end up with the y chi that goes above equilibrium. But you should not trust that solution. This equation is valid as long as the solution, y chi of t, is, let's say, at least one order of magnitude below equilibrium. Otherwise, it's not okay, because you're not consistent with the assumptions you made. Any other question? Yes, you. Oh, because S a cube is constant. And the comoving volume as a comoving volume of size 1 in comoving coordinates as a size a cube in physical coordinates. And S a cube is constant, so you can relate the volume. Yeah, of course, I'm assuming that entropy is conserved, but as you know very well, there are exceptions, right? So these are introductory lectures, so I'm doing Frisin in a standard cosmological background, which is a bath dominated by radiation, and in this case, the expansion is adiabatic, and so the total entropy in the comoving volume is conserved. So S times a cube is constant. Okay. Okay, now this equation gives us the solution, and I want to discuss a couple of things about the solution without giving you the full solution with all the numerical factors. Then we will see one example, but there is something that we need to discuss. And what we need to discuss is the following. Let's say gamma decay is equal to N1 equilibrium gamma. So I'm going to rewrite this. Okay, then there is gamma scattering, N1 equilibrium, N2 equilibrium, sigma B1, B2, chi bar V. Okay? Well, we can, but because it's almost noon and we have lunch at 12:30, so there are several cases, but these are the two most representative ones. Okay, of course, the question is you could also have B1, B2 producing chi in the thermal bath. This is known as the inverse decay. So if you have a heavy chi, okay, then if you produce this chi, then it could decay to B1 and B2, but you could also produce it through inverse decays. That's true, but there are several other exceptions. We will discuss these two just because they feature the interesting qualities that I want to discuss. Where? Sorry. Oh, yes. Yeah, because there is a K2 in this number density, so they have, yeah, thank you. Okay, so let me write again the solution. So in this blackboard, we have the full story. Okay. No, there is a, thank you, yes. This is the one I want to discuss. So we compute the integral the way we usually think about integrals, from left to right, okay? Okay, so this is the situation. We know the solution at any time, and we know the explicit expression of the collision term for these two channels. Now, as the temperature goes down, you have to imagine that we are approaching the present time. And the current dark matter density is given by this equation when you evaluate this equation for T equal to T0, where T0 is 2.7 Kelvin, or 10 to the minus 4 electron volt. Okay, that's what we have to do. There is a huge temperature range from going to T reheat, which is, well, it has to be above the MeV, but it could be much larger, until today, which is 10 to the minus 4 eV. But luckily, we do not have to solve this equation until the present time. And the reason is that, let's take the case of decays, for example. The case of decay has a rate where once the temperature drops below the mass of B1, this ratio of Bessel function doesn't matter anymore. It approaches a constant. But look what happens here. You have an equilibrium distribution of B1. And so if the temperature goes below B1, you start being suppressed exponentially, okay? What does it mean? It means that as the temperature drops below MB1, this gamma goes to 0, okay? And this is the same here, of course. So what you see mathematically, the rate going to 0, as an obvious physical meaning. If I go to temperatures below the particle B1, well, there are no particles in the bath anymore. How can I produce dark matter from the decay of particles that have disappeared? Okay, and so the physical intuition is reproduced by this integral, where basically the integrand is vanishing. Okay, so of course, when you do this kind of solution, you maybe integrate numerically all the way to a couple of orders of magnitude below the B1 mass, but this integral quickly converge, okay? And so we are in a situation where we do not have to extrapolate this. And in some sense, this gives you the picture of a y chi that below some temperature gets to a constant, which is precisely the plot we sketch, freeze out and freeze in. Now, we want to understand how we approach this constant value as we go close to the particle mass. Okay? Yes. Sorry? Oh, sorry. Yes, yeah. I have to put the T only once, of course. Only once. Thank you. Yes. Okay. Any other question or comment? What? I don't understand the... Well, it depends what you mean by freeze out. By freeze out, it means the freezing out of whatever is responsible for keeping thermal equilibrium. So there is never thermal equilibrium in this case. So it's, I would not call it freeze out. Freeze in is you are slowly approaching to equilibrium, but you always fail, okay? So freezing in means you try, but you don't do that. Okay. Okay, so let's try to understand the qualitative behavior of the freezing solution. So let's try to draw that plot. So let's discuss the case of decays, okay, which is simpler. So the case of decays, so let's see, freeze in via decays. So the case of decays is the following. So let's introduce x equal mk over t, okay? Then we introduce xr equal to mk over tr, okay? And let's rewrite that expression as a function of x. Because remember, our plot of y was a function of x. And actually, let me do something else. I just realized that it's more convenient to define x as a ratio between mB1 and T, the temperature. This is, of course, not something that you have to do, okay? And so there is no reason, okay? It's just convenience. If you change variable, it's an integration variable. You can compute the integral with the variable you want. The result cannot depend on the way you compute the integral. But of course, it makes sense to choose variables conveniently. And why is this convenient? Well, I just mentioned that there is this disappearance of bad particles, the one responsible for freezing production via decays. They disappear as a consequence of the Maxwell-Boltzmann suppression when the temperature is more or less the mass of B1. So it makes sense to identify this special moment as x equal to 1. If imagine the dark matter particle is a factor of 1,000 below the mass of B1, then we would have this peak of the production for x values of 1,000, which is possible. There is nothing inconsistent. It's just not convenient. Especially when you work with numerical codes and you want to solve things numerically, it's good to make your choice wisely. Okay. Okay, so let's see. Y chi of x. Now we change integration variables. Okay. So we have from x to xr. Let me do from xr to x. And then I have dx over x. Why is this the case? Because remember, since MB1 is constant, d log x plus d log t is vanishing. Okay, you just compute the Jacobian for the change of variable. So you get the minus sign, you switch again. And this makes sense because xr is smaller than x here if the real temperature is larger than t. Okay? But then let's focus on the fraction between gamma and the cosmological parameters. So we can put, instead of Hubble, we can put Hubble at x equal 1, okay, times what? Remember, Hubble goes like t squared. So this is x to the minus 2, right? So Hubble goes like t squared. So t is the inverse of x. And so I can do the same for the entropy. And then I have gamma as a function of x. Now gamma is here. So let's try to remember. So I have nb1 at x equal 1. So let's compute this integral for x much smaller than 1. Okay. Because after x becomes larger than 1, what happens? The temperature is dropping below, so we have the exponential suppression, okay? So if I want to do an analytical estimate of this integral, let me put myself in the condition where x, not much less, actually, let's say less, okay? So in this case, it's easier because I have n b1 of x equal 1 times x to the minus 3. Why? Because the number density of B in the relativistic regime goes like t cube, okay? And so this is so easy. Then I have the gamma. Of course, the gamma is the decay width in the rest frame. No reason to worry about that, okay? And then I have an additional power of x. Why? Well, this additional power of x is the Lorentz dilation. Okay? So this ratio of Bessel functions, when the temperature is larger than MB1, is MB1 over T, the Taylor expansion, the leading order. So that's basically x, up to factor of 2. Okay? Now, I don't care about factor of 2. I like to understand the behavior of this solution. So I have a constant, okay? I have a constant here. And then I have the integral of dx between xr and x. Now we need to count the power of x. Let's do it together because I may make mistakes. So I guess I have a minus 5 in the denominator. So it goes to the fifth. This x and this x simplify. Okay. So I have 5 minus 3, 2. Okay. And of course, a mathematician would kill me because this is, it's the integration variable. I call x the extreme, okay? So this integral goes like x cube, okay? It goes like x cube as long as x is below 1. So if I try to make a plot, x, and now I call x mb over t, and I call y chi of x, then I have a growth, which in log variables will look like a straight line. Yes? So you ask about the change of variable, right? So you have mb1, which is equal to x times t, right? So you take the differential of both sides, okay? So you get 0, because the mass is constant, and then you get dx times t plus x dt, okay? So you get dx over x equal to minus dt over t. So I had the dt over t there, I have dx over x here, and then the minus sign, I switch the integration extremes. So sorry if I was fast. Okay, good? Okay. Okay. So there is this magic moment corresponding to x equal 1, which corresponds to the moment when bath particles disappear. And so you basically stop having their production. But the interesting part is what happens before, how we approach this constant value. And for freezing via decays, you have this growth, okay? It's a power law growth, which is a straight line in log variables. So you may complain about my integral, because actually this is the proper integral, up to factor of 3, that 1/3, that I don't care. But why did I neglect that? Yes, exactly. So I'm assuming that TR is very, very large, much larger than the temperature I'm considering at the moment. So this integral is valid in the situation where I'm putting myself in a temperature, let's say, even much larger. So I'm assuming there is a clear hierarchy between TR and MB1. Otherwise, this solution, of course, needs to be revised, okay? So if TR is much larger than MB1, I can put myself in between, when T is much lower than TR. But at the same time, I have a full population of relativistic B1 in the bath, okay? And since X is the inverse of the temperature, this allows me to neglect this, okay? So this property is known as, it has a name in the jargon, and is known as infrared domination, which is a nice feature of freezing via decays, okay? So why infrared? Of course, UV and infrared in particle physics have nothing to do with the visible light, which we usually call infrared and ultraviolet frequency. UV means large energy, IR means low energy. So in particular, infrared domination in this context means that the asymptotic dark matter density, this will be Y chi of T0, because it stays constant until today. It does not depend on unknown UV physics, where the unknown UV physics is the reheat temperature here, okay? So as long as the reheat temperature is large enough, I don't care about its value, because my final Rayleigh density will not depend on it. It will depend, of course, on MB1. It will depend on MB1, but that's IR physics in this context. Everything is relative, of course, but if this is the problem, the mass of the decaying particle is IR physics, the reheat temperature is UV physics, and freezing via decays doesn't depend on UV physics. Okay? Any question about this? So let's see. Yes? Oh, you mean here? Yeah, I can integrate from 0 and I get the same. That's IR domination in its full power. When you do a numerical solution, you can integrate actually what people usually do when you have infrared domination. You integrate from 0 to infinity. Why do you integrate from 0? Because you don't care about the detailed value of XR. So integrating from 0 corresponds to taking reheat to infinity, and it doesn't matter. Why do I integrate all the way to infinity? Because there is this Maxwell-Boltzmann suppression of the rate, and so I can extrapolate the validity of this integral all the way down to 0 temperature. Today it's even not 0, it's actually a bit more than 0, but it's very small compared to the energies in this game. But I can extrapolate the integral to infinity. Why? Because I'm integrating over a region where the interaction rate drops exponentially. So I'm basically extending the integral over a region where the integrand is 0. And so you may find this equation from 0 to infinity, and that's okay. These two limits are under control for the reasons I just explained. Yes? Yes? Sorry? I think so. It's fair to say it's assumption of freeze-in. Of course, nothing guarantees that. And if you want, it's a weak point compared to freeze-out, because freeze-out, thermal equilibrium, erases memory. You forget about anything that happened before, and so freeze-out is nice for that. Freeze-in, there is an assumption about the reheating mechanism that doesn't lead you enough dark matter particles to start with. And then if that contribution, it doesn't have to be zero. It has to be smaller than this asymptotic value. So the leading contribution, so if you want, you can write this condition y chi of T0 minus y chi of T reheating is approximately y chi of T0. So if you neglect this contribution to the full solution, you basically get the full solution. So it's a small correction. I mean, they come from two different sources. So it's fair to say it's just an assumption. Until you specify what is the theory of inflation and the mechanism of reheating, you cannot check that explicitly. It's an assumption. Then if you have a framework for inflation and reheating, you can compute the amount of chi you produce and check that it's... So I would say that this derivation holds for the class, for all the inflationary models in the class where reheating does a small fraction. Okay, so you see it's, and other questions? No, okay. Well, you cannot have both, because if you have a freeze out, you are in thermal equilibrium, so the equation of freeze-in is not valid. So either you thermalize, if a dark matter candidate thermalizes at some point in the early universe, it cannot be freeze-in. It's really a distinction you made at the beginning. Well, I mean, at some point, we extrapolate the early universe back in time. We go back, we have this radiation-emitted phase. At some point, something else must be there. I mean, even if once you get to the Planck mass, but there are good reasons to believe, of course, that there is also an inflationary phase. So I would just say, I've been honest. Whatever I told you is true under this assumption. Now, B1 is not the inflaton, of course, because if it's present in the bath after, so I don't think it can be the inflaton. No. Okay, so we are slowly getting to the end of the time, and so let me say the last few words. First of all, the summary of what we said. This equation here, so let's, well, actually, let's leave these two blackboards. So there are a couple of things I want to say before we stop, okay? And before I will make a summary, and then, oops. Okay. So this equation here is valid for any freezing mechanism you have, okay? There is no assumption about being in the decay framework here. The only assumption is that you never thermalize, two separate assumptions. You never thermalize, and you don't make enough at reheating to worry about them, okay? So let me clean this part, and let me give you the full solution for dark matter freezing. This is a solution valid at any moment, okay? It's a solution valid at any moment, and in particular, you can extrapolate its value to today, and as we discussed, this rate drops exponentially because of the Maxwell-Boltzmann suppression of bath particles, so in the end, these integrals can be stopped, okay? And you see, this gamma chi of t is typically a power law before you hit the Maxwell-Boltzmann suppression, okay? And these S and H are also power law, so it's easy to estimate this kind of integrals, okay? So let's assume that gamma chi of t, let's say, is proportional to t to the power alpha, okay? For the decay, we know the explicit value of this alpha. For the scatterings, we need to discuss. We haven't discussed that yet, so that's the next topic. So in this case, and I don't care about prefactors, I want to solve this equation up to a constant. And so if I'm allowed to neglect an overall constant, well, this integral is dt over t, okay? Then gamma of t is t to the alpha, and then in the denominator I have t to the 6th power, okay? Because it's 3 plus 2. And so you see that always neglecting a constant, you have alpha minus 6. So you have t reheat to the alpha minus 5, t reheat, t not reheat, t only t, divided by alpha minus 5. This is the integral, you know, you do the integral, the derivative of alpha minus 5, this alpha minus 5 goes away. So this tells you that the case alpha equal to 5 is somewhat special. And this integral, of course, doesn't make sense. That's something to discuss separately. But as soon as alpha is different from 5, this equation is general, okay? So what do we do with this equation? We notice that y chi of t is proportional to t reheat to the alpha minus 5 if alpha is greater than 5, or t to the 5 minus alpha is if alpha is less than 5, okay? So I'm again assuming a hierarchy between these two temperatures, and so the sign of this exponent is crucial to understand which one of the two will dominate, up to a constant. I don't care about the constant, okay? So let's remember the decay case, okay? The decay case was alpha, in the decay case, alpha was equal to 2, why 2? Because you had the t cube from the number density and 1 over t from the Lorentz dilation. So for the decay case, 5 minus 2, we recover t cube, okay? But this suggests that this infrared domination of freezing, which is a very nice property because it tells me that relic densities do not depend on the reheat temperature, which is something we don't know. It's not always guaranteed, okay? So in this case, you have also the possibility of UV domination, okay? And UV domination, of course, requires to connect your relic density with the reheat temperature, okay? So freezing via scattering, decays, always infrared dominating. Freezing via scattering, well, you can have IR or UV, okay? It depends on the power of alpha. But the power of alpha is set, but what kind of interaction is mediating the scattering? And as an exercise that I leave to you, but that I will put in the notes, just by dimensional analysis, it's a very nice and easy exercise, you can show that IR domination is guaranteed only normalizable. Okay. So IR domination via scattering is guaranteed only if the interaction responsible for dark matter production are renormalizable. Okay, so they are operators with mass dimension at most 4. Okay, and of course, yesterday during the student talks, I heard somebody talking about the gravitino. Okay, there is also another famous supersymmetric particle known as the axino. It's a supersymmetric particle of the axion. These are all situations where the couplings mediating the interaction between these particles and the bath are dimension 5. Okay, and so dimension 5 you feel you fit within this category. Okay, and so in the case of non-renormalizable, you have gravitino, axino, and many others, of course. Okay. So the nice feature of freezing, so the independence of the relic density on details such as the reheat temperature, so this property known as IR domination is always true for decays, but for scatterings you have to check what interactions are mediating. Okay, and now, as I promised, in the last 5 minutes, I will just mention some recent developments that I was part of about freezing. So if you are curious, you can look at these papers, and also you're very welcome to contact me if you have more questions or anything you want to know more about that, okay? So the subject is back to phase space, okay? We solved, well, we started from a Boltzmann equation with explicit dependence on the distribution function, which was integral differential, but somewhat we always managed to avoid solving an integral differential equation. We always put ourselves in a situation where in the end there was just an ordinary differential equation to solve. That was quite easy for the freeze out. For the freeze in, it was not even a differential equation. For the freeze in, it was really computing an integral. Okay, so far the calculations have been very easy. There are situations where, unfortunately, taking one step back to phase space and solving the integral differential Boltzmann equation is necessary. And this is necessary if you care about the cosmological bounds on freezing dark matter mass. Okay, so candidates produced via this mechanism cannot be as light as you want. The reason is that if you produce freezing, let's say via decays, and the dark matter particle is very, very light, you produce this particle with a huge kinetic energy. This kinetic energy will decrease as the universe expands because there is the cosmological redshift. But you want to make sure that the dark matter particles become non-relativistic before it's too late. Okay, too late. What does it mean? It means before they can free stream, they can wash out cosmological perturbations on scales that are too large, inconsistently with what we observe. Okay, so this free streaming effect, which is basically a an effect of washing out cosmological perturbations from overdense region to underdense region just through free streamings, like motion along geodesics, okay? Which is what freezing particles do after they are produced. And if you want to quantify this rigorously, of course, you can make estimates and you can more or less get the order of magnitude where things start to get dangerous. And which is, by the way, one of the reasons why neutrinos cannot work, is precisely this free streaming. If you want to be quantitative about this effect and you want to provide good and reliable dark matter mass bounds, you have to go back to phase space, solve for the distribution function, and use the distribution function to quantify the impact of these particles on dark matter perturbations, okay? And so I leave you with 3 references, and I will highlight the collaborators that made all of this work possible. And I don't remember all the archive numbers, so I will copy them. And 2 of them are from this year, 2 of these reference. Okay, so these are 3 references written in collaboration with Alessandro Lenoci, my former master students, Ariane Decker from University of Chicago, and Tommaso Sassi, currently master student in Padova. PhD student, sorry. Alessandro was master student, Tommaso is PhD student. And so in this first paper, we basically addressed the issue of the impact on freezing dark matter on structure from a model-independent perspective. And we ran Boltzmann solver to compute the matter power spectrum from dark matter through freezing, and we compared this numerical work with analytical estimates, and this formed the basis of everything we did later. This second paper was an update on this model-independent analysis plus an explicit study of specific models of freezing. And then this paper that came out this morning, that's a complete accident, it was not planned, but it's nice that came out precisely today, addressed one of the limitations that is the last thing I want to tell you. Okay, so there was an assumption in all of these lectures. The assumption was a radiation-dominated universe. Okay, so we assume that dark matter production took place during a phase where the universe was radiation dominated. Of course, this is reasonable because it's an extrapolation back in time of what we know, and it's supported by Big Bang nucleosynthesis, because thanks to this extrapolation, we can predict with just one free parameter, the baryon asymmetry, which is consistent with the one we infer from CMB, we can predict the abundance of the light nuclei produced in the first 3 minutes of the expansion history. And so this give us confidence that what we're doing is right, at least back in time until the MEV. Of course, above the MEV, we don't know. It's reasonable, but it doesn't have to be the case. So in this last paper, we explored how the mass bounds on freezing dark matter are affected if you deviate from a standard cosmological history. And in particular, we found that it's possible to relax these bounds. And this is relevant because, and this is probably the last thing I want to say, which is a good message, a positive message, because when freezing was suggested back 20 or so years ago, it was a nice production mechanism because he had the feature of calculability, infrared domination. Then it was like a nightmare for dark matter detection, because if you have a coupling that can not thermalize, it's very difficult to test this. Now, thanks to amazing work done by our experimental colleagues in dark matter direct detection and also at Collider, it's possible to see some experimental signals on freezing beyond this one on large scale structure. For example, you can imagine of producing B1 at collider and observing the B1 decay in the detector, or maybe in some faraway detector that were suggested hundreds of meters from the LHC main detectors. And there are freezing models where now are within the reach of direct detection experiments, or maybe even in the future, okay? So this series of papers identifies where this experimental search should stop, okay? They should stop when dark matter becomes too light because that's inconsistent with the data. And we found with the paper of today that there is some freedom, not infinite freedom, which is good, but you can relax the bounds we found in these two papers just by exploring what an alternative cosmology does. So I leave you with these references. And of course, if you have any questions about the lectures, about the references, feel free to contact me. My email is very easy to find. And I didn't forget, I promise detailed lecture notes that I'm writing. They will not be ready by the end of the week, not even by the end of the school, hopefully by the end of the year. So if you are interested in the notes, only if you're interested, feel free to send me an email at any time. You say, I attended the school, I would like to have the notes. I will make a list of email addresses. And when the notes are ready, I will be very happy to share them with you and get your feedback, okay, to improve, because of course there could be mistakes. So I stop here and I thank you for your attention. I guess we have time for one more question. So there are several candidates. There could be one typical candidate is in frameworks where you have the standard model and then you have a dark sector. Okay, then you have Z2 even. This is like the WIMPs, okay? Z2 odd. The Z2 is the symmetry stabilizing the dark matter. Imagine that this dark sector has some particle that is very weakly coupled. This could be standard model, supersymmetry, gravitino, or axino, okay? But there are many, many others. So here you have thermal equilibrium. So the standard model is in thermal equilibrium with all the supersymmetric particles. I'm mentioning SUSY just to mention an example that is familiar, but it doesn't have to be. And then you have feeble couplings. So you could have that one particle of this state here decays to chi and standard model. This decay would preserve the Z2 symmetry because you have one Z2 odd in the initial state, one Z2 in the final state, and then you produce that through decays. You don't need to have this if you produce chi bar through scattering. Chi bar, in the case of scattering, you can forget about this part, and you can have E plus E minus, for example, to chi bar, and that preserves the Z2 symmetry because you make two of them. But whenever you have something with dashed lines and not solid lines, where solid lines mean thermal and dashed line means not strong enough to thermalize, then you're easily into the freezing. And the nice thing about freezing is that maybe something I didn't emphasize enough, but once you write down the Lagrangian, this production is not optional if you believe in the thermal history. You assume that there are these particles, you assume there are these couplings, you assume there is a thermal bath, the universe does the rest. You do the calculation, but you have no freedom to say that unless you modify the cosmological history. So whenever you write down something with very, very tiny couplings, it's produced by freezing. The question is by how much? And to know that, you have to solve the Boltzmann equation as we did. The simplest one is if you imagine that you have inflation and then the reheating goes through the decays of the inflaton. The inflaton has 0 branching ratio to dark matter. So you populate the bath without dark matter, exactly. So it's not difficult to realize, but of course it's an assumption. It's fair to say it's an assumption. Well, in that case, you have a log, so you produce them at any scale. So it's an interesting case. So in that case, you have to solve the equation, and you have neither infrared domination nor UV domination. You have no. It's the log of the ratio of the temperature. No, it's log TR over T. So it's the log, but you cannot identify a moment where production is dominated. In the UV or IR, you can forget about the value of the other, but in this case, the alpha equals 5. Alpha equals 5 corresponds to a scattering with operator of dimension 4.5. Okay, so that's why the normalizable gives you IR and the normalizable gives you UV, because the threshold alpha equals 5 corresponds to alpha equals 5 to D equal to 4.5. If you do the well, well, actually, it is possible because you could have fractional dimensions, but you could also have Hubble different from T square. In modified cosmology, then the condition becomes different. So there are situations where this is possible. But. Sure. I will be here for 10 more minutes. Thank you. Thank you very much again.